What if I told you that the reason your company's AI bills are just absolutely skyrocketing isn't because the models aren't smart enough?
Right. It's actually because they were terrible at delegating.
Exactly. I mean, think about it. You wouldn't hire, a multi-million-dollar celebrity architect to personally hammer in every single drywall nail on a construction site.
No, you'd go bankrupt before you even finish the ground floor.
Yeah.
Yeah.
But if you were managing AI workflows today, well, that is likely exactly what you're doing. You are either sending every single trivial query to one massive, incredibly expensive model, or you're forcing these models into these clunky, hand-engineered sub-agent networks.
Which, let's be honest, function a lot like highly inefficient middle management.
Exactly. So today on the deep dive, we are fixing that bottleneck. We are unpacking a groundbreaking new framework detailed in a recent paper by Cui and colleagues, and it's titled Uno-Orchestra, Parsimonious Agent Routing via Selective Delegation.
It's a bit of a mouthful, but yeah.
It is, yeah. But basically, we're going to look at how this new system acts as the ultimate AI general contractor, balancing accuracy, cost, and efficiency in ways that previous systems just simply could not do.
Right. And I think the central goal of our deep dive today isn't just to list off the features of this orchestrator. The real breakthrough in this paper is understanding the underlying mechanics.
The actual how of it all.
Yeah, exactly. We need to explore how this system actually learns to optimize this massive, complex trade-off. Like how deeply to break down a task, which specific worker to choose for each piece, and crucially, how to execute all of this while strictly adhering to your predetermined compute budget.
Okay, let's unpack this, because before we explore the solution, we really have to look at the rubble of the current landscape. Like, why is current multi-agent routing so fundamentally broken right now?
Well, primarily it's because token costs are rising astronomically. And, we have this massive frontier of different models.
Right. Some are these hyper-expensive reasoning engines, and others are just cheap, fast summarizers.
Exactly. And the paper outlines two dominant yet severely limited paradigms in multi-agent systems today. Let's start with the first one, which is model routers.
Right.
Model routers operate on what we call a flat routing system. These are essentially single-call routers that make this massive, unchangeable commitment at the very top level of your query.
So you ask a complex question, and the router just picks exactly one expert model to handle the entire thing from start to finish.
Right, which completely misses the parallel structure of a complex task.
Yeah, if I ask a system to, draft an email to my boss about the Q3 budget and also calculate the standard deviation of these 10,000 spreadsheet rows, a model router just sends that whole prompt to a massive reasoning model.
Which is such a waste.
It really is. It's like hiring that incredibly expensive CEO to do basic data entry just because they can do it. Flat routing just cannot trade off the depth of the task against your budget.
It remains completely blind to the internal complexity of the request. It just treats every prompt as a monolith. And, well, to compensate for that exact failure, the industry moved to paradigm 2, which is hierarchical orchestrators.
Yeah, okay, right.
These systems attempt to fix the problem by decoupling the workload. So they separate the decomposition of the task from the actual dispatching of the task.
You introduce a planner module to break the task down into smaller subtasks, basically.
Exactly.
But, that sounds good in theory, but the actual assignment of those subtasks to the workers is where the bottleneck happens, right?
Yeah, because the dispatching is usually hard-coded.
Right. It relies on hand-engineered rules or rigid prompt chains, or it's tied to one incredibly expensive proprietary model acting as the traffic cop. Going back to our analogy, paradigm 2 is like having a rigid assembly line manager.
Right, they write up all the work tickets, but they don't actually know which worker is best at which job.
Exactly, or how much each worker costs. They just hand out tickets based on a fixed rule book.
If we connect this to the bigger picture, the fatal flaw in both of these paradigms is isolation. The two most critical decisions in any workflow, how deeply to break down a task and who specifically to route it to, are currently optimized in total isolation from one another.
Oh, wow. Yeah.
The planner module doesn't know the token cost of the workers, and the dispatcher module doesn't understand the nuance of the overarching plan.
Right. And when those two brains don't communicate fluidly, the result is a system that is incredibly wasteful with compute and honestly surprisingly unreliable when tasks get complicated.
Yeah, and that logical gap really sets up the central question of this research, which is, can a single orchestrator learn, end-to-end, to handle both the decomposition of the task and the routing of the workers simultaneously under an explicit cost budget,
And they answer that with Uno-Orchestra and this brilliant concept they call selective delegation.
which is just a great name.
It is. Uno-Orchestra completely discards the idea of having a separate planner and dispatcher. It is a unified, single causal language model policy. So in the exact same assistant turn, it emits both the task decomposition like the structural plan itself and the routing decision for each individual subtask.
Exactly. And it does this using something the authors call admissible pairs. For every single subtask it creates, it assigns a specific model and a specific primitive.
Well, let's make sure we define those terms clearly for everyone listening. So the model is the noun, like the LLM worker,
Yep.
and the primitive is the verb, the atomic action.
Right. The primitive defines the execution environment. So it could be invoking a multi-step skill, making an external tool call to a search engine, or relying on model internal chain of thought reasoning.
Okay, I follow.
To really ground this, the paper provides a specific example. So imagine feeding the system this query: find places near the Eiffel Tower and Statue of Liberty within a radius of 10 kilometers.
Well, a human looking at that immediately knows it requires multiple distinct steps. I mean, you can't just ask a single database for both simultaneously.
Exactly. And Uno-Orchestra recognizes that complexity and dynamically creates a dependency graph. So subtask 1 is generated, find places near the Eiffel Tower.
Okay.
And it pairs this with a specific search tool primitive and a really cheap retrieval model.
Makes sense.
Then subtask 2 is generated in parallel, find places near the Statue of Liberty. And then subtask 3 is generated, merge those two sets of locations into a final answer.
And crucially, the system explicitly maps subtask 3 to only execute after 1 and 2 are completed, right?
Yes, and assigns it to a model capable of code execution or logical merging.
Wow. But the selective delegation part of the title implies it isn't doing this massive breakdown for everything, right? Like if I just ask it, what is the capital of France?
It gives a direct answer. 0 dispatch cost. It only deploys this complex dependency graph for hard compositional tasks.
Got it. It acts parsimoniously, meaning it is frugal. It conserves its energy and your budget unless the complexity demands it. Okay, I want to push back on the mechanics of this for a second, though, because this is where the paper gets pretty dense.
Sure, go ahead.
You said earlier that it emits the plan and the route in the exact same assistant turn.
I did, yeah.
How is that physically possible without a loop? Like, how is it explicitly choosing the action primitive and the specific LLM model for every single microstep all in one breath without passing data back and forth between a planner and a dispatcher?
What's fascinating here is the underlying transformer architecture itself. Because Uno-Orchestra uses a single shared backbone, the joint distribution actually factors along the token order.
Okay, we definitely need to translate joint distribution factors along the token order for us mere mortals. What is actually happening under the hood there?
Right, okay. Think of how an AI generates text.
Right.
It predicts the next word, or token, one by one.
Right.
By factoring along the token order, the researchers mean that as the language model generates its response sequentially, the plan and the routing decisions are woven into the same continuous string of text.
Oh, I see.
Yeah, they are separated only by causal masking.
Causal masking, meaning the model can only see the tokens it has already generated, like a typewriter that can only read what is already on the paper.
Precisely. As the model types out the parameters for subtask 1, those very tokens immediately become the context it uses to predict the next token, which is the model selection.
Wait, really?
Yes, it uses the context of the plan it just generated milliseconds ago to immediately inform which worker it selects next.
So there are no redundant API calls between a planner module and a dispatcher module at all?
None. It is one fluid, continuous mathematical thought process. And that is the secret sauce for eliminating wasted compute.
Wow. It's like our general contractor writing the blueprint and physically handing out the specific tools to the specific workers in one seamless motion across the room.
That's a great way to put it.
But, I mean, it introduces a massive new problem, doesn't it? You can't just flip a switch and make a standard LLM think sequentially like that. Standard training data sets don't look like dependency graphs with admissible pairs.
No, they don't.
So how on earth do you train a model to become this kind of master delegator?
Well, the training pipeline is where this paper really pushes the boundary. It is a very rigorous two-stage process.
Okay.
Stage 1 is supervised fine-tuning, or SFT. They train the policy on a curriculum of over 61,000 teacher-to-skilled trajectories across 38 public datasets.
Okay. Teacher-distilled trajectories. Let's break that down. So they essentially used a massive, incredibly capable teacher model to slowly work through complex problems, right?
Yes,
Creating perfect examples, trajectories of how a task should be decomposed and routed. And then the smaller Uno-Orchestra model just studies these 61,000 perfect examples to learn the behavior.
yeah, but with a massive caveat here. These aren't just simulated text completions happening in a vacuum.
Oh.
The code and tool subtasks generated by the teacher were executed in real sandboxes.
Really? Meaning if the teacher model suggested using a Python script to scrape a website, the training environment actually ran that Python script.
Yes. The observations the model learns from are actual runtime outputs. If a tool fails in the real world, the training data reflects that failure.
That's incredible.
It is. The AI is learning from real-world environmental feedback, establishing a grounded foundation of what actually works, rather than just learning to mimic a static data set of, correct-sounding text.
Okay, so that sets the baseline. But an AI studying past examples will eventually hit a wall when faced with something entirely new, right? Stage one is just observation.
Right, which brings us to stage 2, which tackles what they call the residual hard pool.
The complex tasks that the base model still failed at, even after the supervised fine-tuning.
Exactly. To conquer these, the researchers utilized a multi-turn extension of reinforcement learning called agentic GRPO, which stands for Group Relative Policy Optimization.
Okay, here's where it gets really interesting, because to understand why they had to invent a new form of GRPO, we have to look at a massive flaw in traditional reinforcement learning called the credit assignment gap.
Oh, it's a huge problem. In a multi-turn agentic rollout, an AI might make dozens of individual decisions. It might plan 5 subtasks, pick 5 different models, execute 5 different tools.
Right.
The problem with vanilla GRPO is that the binary signal that tells the AI it did a good job only arrives at the very termination of the task.
Yeah, so think about it like a basketball team winning a game. If you train a team using vanilla GRPO, the coach just walks into the locker room at the end of the game and gives everyone a generic good job medal because the final score was a win.
Right.
The player who made a terrible turnover in the second quarter gets the exact same reward as the player who hit the game-winning shot.
Exactly. In the context of our orchestrator, vanilla GRPO rewards the entire trajectory. It leaves all those early routing choices completely unsupervised.
So the AI has no idea which of its 10 micro-decisions was the actual genius move that solved the problem and which ones were just wasted compute.
Precisely.
Yeah.
And agentic GRPO fixes this.
So instead of a generic medal at the end, it's like a coach sitting down, watching the game tape frame by frame, and explicitly rewarding the specific player who made that crucial, highly contested pass in the first quarter that set up the momentum for the winning shot.
That's a perfect analogy. Mathematically, agentic GRPO solves the credit assignment gap by taking a portion of that final terminal reward and routing it backward through the trajectory to each individual turn.
Okay.
Furthermore, it augments that reward with a bounded shaping signal.
A shaping signal. Now, this is where they introduce the parameter eta, right? This is the reward specifically tied to cost efficiency.
Yes. Credit is attributed at the granularity of individual orchestration decisions. So the model gets a reward not just for being right, but for being efficient.
But, I mean, anytime you introduce an efficiency reward, you risk the AI gaming the system, right? Like, if it gets a dopamine hit for saving money, won't it just start picking the absolute cheapest, worst models for every subtask just to maximize its efficiency score?
Oh, absolutely. And the researchers anticipated that exact failure mode.
Oh, they did?
Yeah. The math is carefully balanced so that the shaping reward, that eta parameter, is kept deliberately small. It is mathematically bounded so that it can never overpower the verifier.
The verifier being the ultimate judge of whether the final answer was actually correct?
Correct. So by capping the efficiency reward, they explicitly prevent the policy from harvesting cheap and wrong cost bonuses. Accuracy remains the dominant, non-negotiable goal, and efficiency acts as a secondary optimization pressure.
Wow. Okay, so we have an elegant single-turn causal architecture, and we have this incredibly nuanced reinforcement learning pipeline that solves the credit assignment gap.
Right.
But as we know, all of this advanced theory must ultimately be judged by its real-world performance. A model can be elegant and still fail at basic math. So let's look at the actual numbers they publish.
Let's do it. They evaluated Uno-Orchestra across 6 distinct capability axes to ensure it wasn't just a one-trick pony.
Okay, what were they?
They tested atomic reasoning, compositional reasoning, knowledge retrieval, multi-hop composition, tool and code use, and agentic and long context tasks.
I mean, that covers basically the entire spectrum of enterprise AI use cases.
Pretty much. And they subjected it to a massive 13 benchmark suite, including heavy hitters in math, code, and knowledge retrieval.
The result.
The system reaches a 77.0% macro pass at one rate.
Okay, let's define macro pass at 1 for our listeners, because this isn't grading on a curve.
No, it's not.
Pass at 1 means the percentage of times the system completely solved the complex task, from start to finish, on its very first attempt, with 0 human intervention or retry prompts.
Exactly.
Hitting 77% across that diverse of a benchmark suite is massive.
It is. It is roughly 16% above the strongest workflow baseline they tested against.
Wow.
And a 16% absolute jump in multi-agent orchestration reliability is just a generational leap. But honestly, the truly disruptive finding isn't just the accuracy jump.
Yeah.
It achieves this 16% improvement at roughly an order of magnitude lower per query cost.
Wait, 10 times cheaper.
Yes.
It is 16% more accurate, and it costs 10 times less to run.
It significantly advances what the researchers call the accuracy efficiency frontier. And it achieves this optimization through its objective function, which introduces an alpha parameter.
The alpha parameter. Okay, so this is essentially a literal slider for developers, right?
Yes. The alpha parameter explicitly trades off correctness against cost. The model actively evaluates the token-level cost, which is denoted as C of P of every worker model in its admissible pairs.
So what does this all mean? For you, for your engineering teams, for the industry as a whole? It means the era of brute-forcing complex tasks is ending.
Right.
Taking your most expensive, massive, trillion-parameter LLM and throwing it at every single basic prompt is economically unsustainable.
Totally.
And as this paper definitively proves, throwing a massive model at a complex task is actually less accurate than a smart delegation system breaking that task down.
This raises an important question, though. You have to consider what it truly implies when an AI orchestrator is imbued with a literal sense of budget awareness.
Yeah, that's wild to think about.
It is. It can look at a subtask, realize it's just a simple formatting issue or a basic web search, actively choose a model that costs fractions of a penny instead of dollars, and optimize the entire trajectory cost without a human engineer having to write a single line of routing code.
It's treating compute as a finite, precious resource to be managed, not just some infinite well to be drawn from.
Exactly.
Well, let's take a breath and recap the journey we've been on today. We started by looking at the deep flaws of flat routing, sending everything to one model, and the bottlenecks of rigid hierarchies where planners and dispatchers don't talk.
Right.
Then we discovered how Uno-Orchestra utilizes a single causal language policy to dynamically decompose and route tasks via selective delegation, generating the verb and noun in one continuous token stream.
Yeah.
We unpacked its rigorous real sandbox training and how agentic GRPO acts like that meticulous basketball coach, solving the credit assignment problem by rewarding specific microdecisions.
Which is key.
And finally, we revealed that it achieves a 16% boost in absolute accuracy while slashing compute costs by a factor of 10.
It is just a remarkable achievement. But, I want to leave you with a lingering thought to explore on your own.
Oh, please do.
The entirety of this research relies on a closed pool of frozen worker LLMs and predefined routing primitives. The orchestrator has a fixed roster. It knows exactly who is on its team and exactly what tools are in the toolbox.
Right, it's a static universe of options.
But what happens when that pool becomes open?
Oh, wow.
Imagine a future iteration of a system like Uno-Orchestra that hits a subtask, realizes it doesn't have the right tool or the right worker in its local pool, and dynamically writes a new primitive on the fly.
That's terrifying and amazing.
Or what if it actively searches the web, navigates to a repository, finds a completely unseen, hyper-specialized open-source model, integrates it via API in real time, and delegates the task to it?
The orchestrator wouldn't just be delegating to a pre-existing team anymore. I mean, it would be dynamically building its own workforce out of the entire global ecosystem of AI.
Exactly.
It could assemble and disband specialized digital corporations in milliseconds.
It shifts the paradigm from managing a team to creating the team dynamically based on the exact contours of the problem.
That is a staggering thought. You don't just have a general contractor managing the workers on the site. I mean, you have a general contractor who, upon realizing they need a completely new type of glass installed, invents the glass, invents the tool to cut it, and then instantly recruits the one entity on Earth who can install it all before the cement even dries.
That's exactly it.
It is a completely different paradigm for how we will build and interact with intelligence. Well, thank you so much for joining us on this deep dive into Uno-Orchestra. Keep exploring the limits of these tools, keep questioning the mechanics of the technology around you, and we'll see you next time.